Hello, metallurgist. Welcome back. This is part two of an episode covering welding of cast iron, the impossible. But my guest, he has developed a solution that can work and where it's possible to weld on very big structures in cast iron. So you should really look forward to this. Enjoy the show. Thank you. Hi, Masoud. Welcome back to part two of the talk about welding of cast iron.
Hi, Peter. Happy to
Yeah,
see you again.
yeah, you too. Masoud, in the last talk, we went through all the reasons why it is impossible to weld in cast iron. Uh, but you promised that you would show how you have developed a solution for it. So what is the secret behind the welding method?
Actually, the secret is to go deep into the cracking mechanism to
Hmm.
understand why the crack appears and how the crack initiated and propagated in the different zone. As I said in the first episode, I said that we have four cracking mechanism. One is a base metal cracking, heat affected zone cracking, heat affected zone and partially melted zone cracking, fusion zone cracking. And also in one situation, we have a problem that this crack join together to form a really large crack.
Okay.
So, and so we start to work how we can eliminate how we can disactive any
Hmm.
every mechanism that activate the cracking.
Yeah.
Actually, as you know, when a material is unweldable and it's difficult to weld, the already suggests that there is a recommendation to use the low heat input procedure, welding procedure,
Hmm.
to reduce the amount of the heat that you induce in the
Mm.
workpiece. But in the ductile cast iron, if you use a really low heat input specimen using conventional welding method, I don't talk about the laser welding or
No.
electron
Mm.
beam, something that
Mm.
can be used in any workshop
Hmm.
using GMAW process, using flux core welding process, GTAW,
Mm.
conventional welding process,
Yeah.
is that if you use low heat input process, base metal cracking and fusion zone cracking will occur. But
Okay.
if you increase the heat input to
Mm.
eliminate the problem with the fusion zone cracking, you have a really wide heat affected zone and also partially melted zone. So the
Mm.
crack will appear because of the brittleness in this brittleness and the
Yeah.
brittle structure is in this region.
Mm.
So there must be a solution to solve the problem. Actually, we use thermocalc simulation to
Hmm.
see how we can, as you, thermocalc simulation is used some thermodynamic calculation in the equilibrium and non-equilibrium.
Mm.
Actually, for the welding, we use child method to predict the component that can be formed in the fusion zone. So
Hmm.
because one of the recommendation for the welding of the cast iron to find the proper filler material, we
Mm.
cannot use normal filler material for casts, uh, welding of the steel or using the similar filler material for
Mm.
cast iron.
Mm.
So it's recommended to use a filler material with the amount of the nickel content,
Hmm.
but the dilution is the problem.
Yeah.
How much contribution from the base material should be involved inside the filler in the fusion zone
Mm.
to select the right filler material. So we find that to eliminate the problem with the, and also we need a filler material
Mm.
that can absorb the stresses.
Yeah.
So it
Mm.
means that we need a soft filler material.
Mm.
But we cannot use soft filler material for the whole grooves, for the to filling up the grooves, because in that case you have a problem with the final mechanical properties.
Yeah. Okay. Then we have the which. Yeah.
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 So the welding become the weak point
Mm-hmm.
in if you use the really soft material.
Yeah.
But it's possible to use the soft filler material just for depositing on the first layer where there is a contact between the filler material, weld metal, and the base material, which
Okay.
is called buttering technique.
Mm-hmm.
Yeah.
Yeah.
So
And and what is the content of that? The chemical composition of that filler?
actually, it's close to the more than 90% nickel.
Okay.
Okay. And the dilution was in the range of the 30 to 40%. So there
Mm.
must be a optimization of the welding parameter to limit the dilution of the base
Yeah.
material, to limit the melting of the base material,
Mm-hmm.
to avoid importing carbon from the base
Yeah.
material into the fusion zone.
Yeah.
And also, we find that when we use high nickel content based on actually this 30% dilution, we find it through the thermocalc analysis. Because
Mm-hmm.
if you have a dilution more than this amount,
Yeah.
30 and 40%, the mechanism is completely different for the solidification of the fusion zone, and you have a problem.
Yeah.
Yeah, because
Mm.
the final constituent, a final product of the fusion solidification is important to avoid cracking.
Mm-hmm.
So you need to limit the dilution,
Yeah.
and that is one of the findings using thermocalc analysis.
Mm-hmm.
So
Uh, but what is happening? You have a ferritic structure, and you add a lot of nickel. That will give you an austenitic phase. But what
yes,
happened when you dilute the austenitic nickel phase with more than 30% of your base material? What
okay.
microstructure will appear in that?
The macrostructure is the matrix is austenite,
Mm.
but depend on the dilution, you can get the cementite in the interdendritic area or
Yeah.
graphite.
Mm.
So if you get cementite, and the cementite is a low melting temperature that is a brittle structure that
Mm.
can cause a fusion zone cracking.
Okay, it
So
goes to the grain boundaries.
yeah,
It's
exactly
pushed
to
out, so
the
you have grain boundaries with
mhm,
cementite.
yeah,
Yeah.
exactly.
Hmm.
And but if you control the dilution, you
Mm.
can end up with the austenite and graphite
Yeah.
because nickel cannot dissolve the carbon inside. So
Hmm.
that carbon must be appear as a something. So
Yeah.
this is the graphite here. So
Ah.
if you have a graphite, you don't have a problem with the
Mm.
fusion zone cracking in the first layer.
Yeah.
Okay. And also this nickel, this soft fusion zone, absorb the residual stresses, so it helps
Mm.
to avoid cracking.
Yeah.
And another finding is that has already published it, that when you use high nickel content with the low dilution, this nickel content can penetrate into the partially melted zone. So because the partially melted zone is a
Mm.
semi-solid, is a partly melted.
Yeah.
So so it's
Mm.
possible that the element can penetrate into, and when the nickel penetrate into the partially melted zone, it avoid the formation of the wide partially melted zone containing Ledeburitic structure
Ledeburitic. Yeah.
that
Yeah.
is really brittle. So
Yeah.
with using of this filler material, you avoid the formation of really brittle structure in the partially
Mm.
melted zone.
Yeah.
But you still have a problem in the heat affected zone.
Hmm.
And the problem is that when you want to limit the dilution, you use low heat input process. And when you use low heat input process, it means that the cooling rate is still high. And the high cooling rate results in the brittle martensite on
Mm.
temperate martensite.
Hmm.
So it's still the problem.
Yeah.
So um, So we need a process that temper the martensite, but we cannot use post-well heat treatment.
Yeah, not these big parts.
Yeah. So the solution is that we use something that is called temper beat technique. We use the heat of the subsequent welding passes to temper the heat affected zone.
Okay. So you add extra heat in
Yes,
second pass.
yeah, on the second layer.
Yeah.
So
Mm.
this is completely in the opposite side of the recommendation in the
Yeah.
standard or everywhere that
Yeah.
is don't use high heat input for the welding of ductile cast iron.
Yeah.
But the reason is that we have a barrier between the high heat input filler material
Mm.
and with the base material, that is the buffering layer. So there is no contact melting between the
Mm.
base material and there is no contact between the second layer and the base material.
Mm.
So that this high heat input cannot have adverse effect on the heat affected zone problem.
Okay.
So, and the tempering effect is around 300 Vickers in the heat affected zone.
That's fair.
Yeah,
A lot different than the 800 you had before.
yeah.
Yeah.
800, so it can reduce to the 500 to 600.
Yeah. Hmm.
And also, when you use high heat input, so for the next layer, for
mm.
the next layer we call it filling up filling layers.
Yeah.
You cannot use nickel filler material because of the low strength, because you need a
Okay. Yeah. Yeah. Of
component
course.
that can have a
Yeah.
high strength. It always recommended to use a filler material with the strength at least equal to the base material. So
Hmm.
you need to use a high strength filler material.
Yeah.
And now you can add some iron into your filler material to
Mm.
increase the strength.
It's also cheaper.
Yeah, of course, it's also
Yeah.
cheaper.
Yeah. Uh, so do you vary it from layer one, 90% nickel? Then what is layer two? Is that 50? And then
Yeah, it's gradually decrease
yeah.
because in the first layer, no, for the filling up layers, we use the
Mm.
one filler material because we don't need to change it several times. But
Okay.
because of the dilution of the second layer with the first layer, we have a different
Mhm.
nickel content in the
Yeah.
second
Okay.
layer.
Yeah. Mm. Yeah. What is the chemical composition of the second layer or the second filler?
Second filler is half nickel, half, but
Okay.
iron,
Yeah.
but it's not half, 40 nickel,
Okay.
40, yeah.
Mm. Yeah. How does it look after doing that? Do you have a picture you could show?
Yeah.
That could be
Yes,
pretty interesting to see.
okay, let me share my screen. I should, as you can see, I show in the first episode that
Yeah.
this is the first step into the wellcast project that
Mm.
we use 200-degree preheating
Yeah.
temperature, and there are a lot of cracks everywhere.
Hmm.
And this is one of the not the final result, but the close to the final result that you can see. There are some really minor crack here, but we
Yeah. In the
use
middle.
no pre, yeah, but we
Hmm.
use no preheating,
Yeah.
and the welding start at room temperature.
Mhm. Yeah.
And as is why I want to show you the hardness differences, as you can see,
Yeah.
the maximum hardness
Yeah.
at the
Around
bottom layer after,
700. Yeah.
yeah, the hardness reduce it
Yeah. So the
clearly.
Ledeburitic structure at the 1100 Vickers is gone.
Yeah,
Mm. Yeah.
actually, in this project, it's not uh, when we done this, there are a lot of workshop around the world that work on the welding of cast iron.
Mm.
But the problem is the final mechanical properties, especially the fatigue property. It's
Okay.
not enough to show a
Mm.
cross section that there is no crack,
Hmm.
because you can use some filler material that there is no crack in
Yeah.
the weld metal,
Hmm.
and you say, okay, there is no crack, so this is the solution. But
Mm.
since we work this project with some partners in the wind turbine industry, like Vestas and Siemens, the
Mm.
mechanical properties was really important. So we have made a lot of fatigue testing,
Okay.
and the result is actually we made several optimization, but we still need some optimization if there is any second project,
Mm.
because the first project has already concluded. And the result really surprising and acceptable in the high cycle fatigue,
Hmm.
and it can pass the requirement in both Vestas and Siemens
Yeah.
requirement.
Yeah.
But for the situation where low cycle fatigue happen, we need more optimization
Okay.
to avoid premature failure.
Mm. Yeah. Is it the at low cycle? Is it because you go to a higher peak?
Yeah,
Yeah. Okay.
exactly.
Yeah. Mm.
But mainly the high cycle fatigue is a dominant fatigue loading in the wind turbine, but low
Yeah.
cycle always happen, shutdown and a start or something like that.
Yeah. Or the storm of the year.
Yeah, exactly.
Yeah.
Can make a
Yeah.
problem.
Mm.
And why we work on the conventional welding process? Because we wanted to develop a procedure that can be used in the any foundry. Because
Mm.
maybe
Yeah.
somebody say that, okay, you can use laser, you can use electron
Yeah.
beam, but
Hmm.
it's a really huge component. You
Yeah.
cannot bring it to the small room of the
Mm.
laser and
Yeah.
try to welding, and is the capital cost for this investment of this equipment is really
Yeah.
high.
Yeah.
And we had a crazy idea that if there is a crack during the
Mm.
operation, how we can fix it. So there might be a solution to go up tower, a welder team, two
Ah.
person
Yeah.
with the a small welding equipment
Hmm.
inverter, go up
Yeah.
and fix it.
Yeah. And some
But
filler in your back.
yeah, exactly.
Yeah.
So, and also another idea is that if we can weld the uh, cast iron, not
Mm.
repair welding, welding the part. So as I said, this component is really huge. So
Mm.
suppose that the situation that we can cast them in the small pieces.
Hmm.
And as you know, I
Yeah.
said that the transportation is a problem. I-
Hmm.
In the first episode, the transportation of the huge component is a problem. You
Yeah.
need a special and permission in the
Hmm.
routes, and
Yeah.
also you need a special vessel to ship them from the Asia to the Europe.
Yeah.
So support that you make them in the small pieces, and you have
Hmm.
a small workshop close to the wind farm,
Yeah.
and try to weld them at the
Yeah.
a small workshop next to the wind farm.
Yeah. So make it as an assembly instead of in one piece.
Yeah,
Yeah.
exactly.
Hmm.
This
Yeah.
is a crazy idea that I hope will happen in the
Yeah.
future.
Yeah. Uh, do you have a timeline for when will it happen? Has it already been introduced industrially, or will it be over the next years? Well, how do you see the timeline for it?
Actually, in the Wildcats one, the project that I was involved with, we reached TRL 5 or 6. So it's still has some step to go into industries. And there was an
Mm.
idea to continue the project in the part 2. But as you know, some partners are not in good economy. And the team that we had in DTU is completely gone, and the people
Mm.
scattered to the different companies.
Yeah.
So I hope it can. And also, I left DTU and Vestas to join MAN. So I don't
Mm-hmm.
know what happened. But if there is a investment from the both side of the universities and also industries and
Mm.
foundries, it would be happen.
Yeah.
I'm sure that, but maybe in the timeline of because the, there is a problem with the cast iron. Let me share with you.
Yeah.
The cast iron is a
Only
material
one
that
problem.
no, it's a one of the problem.
Okay.
The cast iron classified based on the mechanical properties. It's not they're not classified based on the chemical composition similar to the other material. So
Hmm.
did you notice that? So why
No.
this is because the range of the composition for the cast iron is wide, and the the foundries has their own recipe for casting of the component and
Hmm.
give you the same grade that you want. For
Hmm.
example, it's common that you ask for the grade 500-14 from several foundries and you receive it and the grade is compatible with the requirement of the mechanical properties, only tensile properties, because the classification is based on the mechanical properties. But
Hmm.
the nodule size, nodule count,
Yeah.
and distribution, and also the
Hmm.
morphology of the nodule, the percentage of the chunky graphite
Yeah.
can be different.
Okay.
And the same grade and the
Mm.
same grade of the cast iron from the several foundry can end up with a different, completely different fatigue
Of course.
properties.
Yeah.
And
There must
also
also
welding.
be a difference when you cast the same alloy in small parts or in very big parts,
Exactly.
because the segregation when you solidify
Mhm.
over a long period must differ in the microstructures. You might have more
Mm.
chunky
Yes, exactly.
and lamels when you have long time for it.
And it's also happen when you have a thick section,
Hmm.
the composition, the distribution of nodule is completely different in the core and in the surface.
Exactly. Yeah.
So, and also the welding uh, metallurgy can be different when you have a different kind of the nodule. As
Yeah.
I understand, the chunky graphite can make a problem for
Hmm.
the welding.
Yeah.
And the size of the nodularity, the circularity of the nodule can
Mm.
affect on the welding properties.
Yeah.
And also the count of them is that they are small or they are big. It
Mm.
can affect on the, especially in the heat affected zone.
Yeah.
And also
Mm.
when you have some flake graphite, it can affect on the in the base material cracking
Mm.
and the heat affected zone cracking because the sharp edges can work as a stress concentration point. Because as you
Mm.
know, the another problem in the cast iron is that
Mm.
it's the composite material, but there is no metallurgical bond between the matrix and the nodules.
Hmm.
So they are completely, it's like
Yeah.
it's like Husina in the cookies.
Yes.
Yeah.
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 Yeah. So it's if the nodules had a higher what is that called, thermal expansion, then it could be loose and you can hear it on the inside.
Yeah. Yeah.
Mhm.
Exactly.
Yeah.
And when you have a chunky graphite, they can
Mm.
easily release the carbon into the heat affected zone.
Yeah.
When you have a really small graphite and
Mm.
like a chunky graphite or really a small nodule, they easily release carbon into the
Mm.
uh, heat affected zone because
Mm.
they easily dissolve it
Yeah.
into the partially melted zone and heat affected zone.
Mm.
So I don't think so if it's possible now to develop a general solution for all kind of the cast iron from
Mm.
all foundries that can work for everybody. It somehow must be customized.
Yeah. But then it could also be a good recipe that every casting unit had their own facility to do it.
Yes, exactly.
Yeah.
They cannot cheat from another foundry. They must go through deep into that by themselves to
Yeah.
see what kind of cracking mechanism will be activated and
Exactly.
how they can solve this cracking mechanism.
Yeah. Masoud, I have one last question. If people want to learn more about this, where could they find? Should they look in literature? Should they call you? Should they go to a conference, or where could they find more information?
Actually, everybody are welcome to call me. No
Yeah.
problem. I'm open to receive calls. And also in the next DMS winter meeting, Danish Metallurgical Sales Cave, I will present some of part of the result. So
Mhm.
everybody that's interested can join there.
I'll
Actually,
be there.
I'm the last presentation. So when everybody is about to leave, I present
Yeah.
something.
Yeah.
So,
Mm.
and also we publish several paper and the solution will be published soon and the cracking mechanism will be published soon, but I'm a bit lazy to finish the papers.
Okay.
So I try to finish them as soon as
Yeah.
possible.
Perfect. I will post the papers you have published in the comments in the YouTube video, so people
Yeah,
can find the link there.
yes, but the paper that we published several papers, two of them on because the welding is the both metallurgy and stress. So we had another colleague that worked on the residual stress
Mhm.
simulation. So we
Yeah.
published two paper on the residual stress distribution and also one in the metallurgical behavior and the microstructural evolution when we use pure nickel filler material or half nickel
Mm.
filler material. And also I published one in the conference regarding the challenges during the welding of ductile cast iron. And yeah, you can use them in your channel. And if anybody interested, you can place my email address and
Perfect.
everybody's welcome to call me.
Wonderful. I'll do that.
Yeah,
So thank you very much. I
yeah,
learned a
you're
lot
welcome.
today.
Yeah,
So I
thank you.
really enjoyed it.
Yeah, it's a
And
great honor for me to be a part of your everyday metallurgy.
I'm so happy. And I really hope that people will reach out to you, because the platform is meant for sharing and learning
Yes,
in
exactly.
the community of metallurgists. So
Yes,
thank
true.
you for sharing your knowledge.
Yeah. Thank you for your calling me and also for this episode, everyday metallurgy that you have. I really interested in that one, and it's really good idea that you change from Danish to English. I
Yeah,
really appreciate that.
that was necessary.
Yeah,
Yeah.
great. Thank
See
you.
you.
See
Yeah.
you later. Bye.
Bye. Thank you very much for following the episode on welding of cast iron. Masoud did the impossible. And another thing that is pretty difficult is to build up a community of metallurgists that are willing to share what they do and are willing to comment or help each other. But I really believe that this platform, the podcast Everyday Metallurgy, can be the place to share and build up a community. So please, if you want to be a part of that community, subscribe and share and give your comment. Everybody who participate on the podcast, they are asking for questions. They are willing to share, and they are here because they also want to learn. So open up and give your comments. Thank you very much.